So, let us continue our discussion on phase portraits of higher order systems. In the previous lecture, we took examples from the third order systems, and we tried to establish an analogy between second order and third order systems, and how we can extrapolate the observations from second order planar systems to the third dimension. Today, we will take an example from fourth order system. So, what we have in front of us is an equation, a dynamical equation with 4 components x 1, x 2, x 3 and x 4. The equations are given in front of you. So, the first thing that we would like to do is to convert this equation, this set of equations to a matrix equation, and I can identify the dynamical vector as x 1, x 2, x 3, x 4. This would be multiplied by a matrix, and you would get x 1, x 2, x 3, x 4 back. Okay. So, what would be the elements of the matrix? This would be 1, 1, minus 1, 0, 0, 1, 0, 1, 0, 0, 1, 1 and 0, 0, 0, 1. Okay. So, these are the elements of the matrix. Now, I have the matrix equation of the form dx under bar by dt is equal to a double under bar x single under bar. And then we saw that by using the theorem that the solutions are given as summation I going from 1 to n C I e to the power lambda I t V I under bar, you can in fact solve the equations of any order. So, these equations involving 4 variables might in general seem to be quite daunting, but it is not as difficult as it looks like. So, what do I need to do? The first thing which I need to do is to determine the eigenvalues. So, I have eigenvalues in front of me. In fact, for this particular example, there is only one eigenvalue. Okay. And what are the eigenvectors? Let me write down the eigenvectors. I have only 2 eigenvectors. V 1 under bar is 1 0 0 0 transpose, and V 2 under bar is 0 1 1 0 transpose. Now, we are in trouble, because we saw that our solution went as 1 I going from 1 to capital N, which means we assumed that we have all the eigenvalues available with me, which are linearly independent, and they are equal to the number of variables which I have. In the current case, that is not the case, and therefore, the first thing which you need to do is, since n is equal to 4 in this particular case, what you need to do is, you need to determine the rest of the eigenvectors. So, therefore, you will need 2 generalized eigenvectors. I assume that you have revised the method to determine the generalized eigenvectors. I will write the generalized eigenvectors here. Please make sure that you confirm that this is also what you get. So, I will write generalized eigenvector V 1 g, because that is the eigenvector which I will get from V 1. Okay. So, V 1 g is 0 1 0 0 transpose, and the generalized eigenvector V 2 g, the eigenvector which I would get from the second eigenvector would be 0 0 0 1 transpose. Okay. So, now I have 4 eigenvectors which are available with me. Let us see how do we proceed from here. In general, I would have written the solution as x 1, x 2, x 3, x 4 as summation I going from 1 to capital N C I e to the power lambda I t v I under bar. I do have 4 eigenvectors, but now I cannot use this formula simply like this anymore. Instead, for the case of repeated eigenvalues and when you do not have sufficient number of eigenvectors, this is what you will need to do. Okay. So, remember that I have eigenvector v 1 under bar. From v 1 under bar I got v 1 generalized under bar. I had v 2 under bar. From v 2 under bar I got v 2 generalized under bar, right. So, the way I modify equation A for getting the solution under this case is I do this x 1, x 2, x 3, x 4, this would be equal to C 1 e to the power lambda 1 t. In fact, in this case we have only one lambda. So, let us not worry about the index of lambda e to the power lambda t, otherwise if you do not have, you will have to multiply it with corresponding eigenvalue. Okay. This would be multiplied by the eigenvector 1, the original eigenvector, okay, plus C 2, the eigenvalue remains the same. So, I will write e to the power lambda t. Now, the second term will be such that you would have t, the independent variable, multiplied by the original eigenvector, remember, plus the generalized eigenvector v 1 g. Okay. Then going for the effect of second eigenvector and second generalized eigenvector, I can write C 3 e to the power lambda t v 2 under bar, simply the effect of independent eigenvector which you originally had, plus C 4 e to the power lambda t, the original eigenvector, linearly independent eigenvector v 2 under bar, plus v 2 g under bar. This is the formula. Formula 1 for the linearly independent eigenvector, formula second given by B is when you make use of generalized eigenvectors. So, let us write down the solution. What would the solution be? X 1, x 2, x 3, x 4, this is equal to C 1, the eigenvalue is simply 1. So, e to the power t times the first eigenvector, first original linearly independent eigenvector. So, that eigenvector was 1 0 0 0 plus C 2 e to the power t multiplied by t times the first eigenvector, which means 1 0 0 0 plus the second the first generalized eigenvector, and the first generalized eigenvector that I had was 0 1 1 0. Fine. Then plus C 3 e to the power t, this would be equal to the second eigenvector. The second eigenvector was 0 no. So, we I think made a mistake in writing the generalized eigenvector. This was not the generalized eigenvector. So, first generalized eigenvector was 0 1 0 0. Okay. Now, I have second eigenvector which is 0 1 1 0 plus C 2 e to the power t multiplied by the first the second eigenvector, this is 0 1 1 0 plus simply the second generalized eigenvector, this was 0 0 0 1, right. So, I can simplify this as C 1 e to the power t 1 0 0 0 plus C 2 t e to the power t 1 0 0 0 plus C 2 e to the power t 0 1 0 0 plus C 3 e to the power t 0 1 1 0 plus C 2 t e to the power t 0 1 1 0 plus C 2. Okay. So, there is one problem of this index, this should be C 4, this should be C 4, and therefore, here you should have C 4, C 4, this should be C 4 e to the power t 0 0 0 1, fine. So, this is the expression for x 1, x 2, x 3, x 4. So, what will you will do? You will solve, you will simplify this expression and write down the individual values for for x 1, x 2, x 3, x 4. In fact, I have the final simplified expression for you. So, please do this simplification and see if you get the same answer. X 1 should be equal to C 1 e to the power t plus C 2 t e to the power t, x 2 is C 2 e to the power t plus C 3 e to the power t plus C 4 t e to the power t, x 3 is equal to C 3 e to the power t plus C 4 t e to the power t, and finally, x 4 is equal to C 4 e to the power t. So, what we saw was that this seemingly difficult set of simultaneous equations or set of equations governing the dynamics of fourth order systems can in fact be solved easily using matrix method. Now, in all of our analysis, what we did was that we always had the case right from the beginning where you had the equilibrium solutions as 0 0 or 0 0 0 or in this previous case 0 0 0 0, okay, which means that the origin was always the equilibrium solution. When we took the example of a first order system, dx by dt is equal to Ax, x equilibrium was 0. When we took the examples like this, dx by dt is equal to x 1 x 2 is equal to A B, C, D, x1, x2, the equilibrium solution x1 equilibrium, x2 equilibrium were 0, 0. We saw this to be the case for third order systems as well, which means for autonomous systems 0, 0, 0, 0 is always an equilibrium solution. In certain cases we found that the equilibrium solution was stable, in certain other cases we found that they were unstable. But now the question is it always true that you will have only and only 0, 0, 0, 0 as the equilibrium solution? Can you have a system where the origin is not only the solution, not only the origin is the solution, but you have other solutions also which are equilibrium solutions? So, let us take an example and see if this is the case. So, I have a dynamical third order system which is given as dx1 by dt is equal to x1 plus 2x2 minus 2x3 dx2 by dt is equal to 2x1 plus 5x2 minus 4x3 and dx3 by dt is equal to 4x1 plus 9x2 minus 8x3. Now, to analyze this system, what I will do is I will convert this to a matrix equation. So, I have d by dt of x1, x2, x3 and this is equal to 1, 2 minus 2, 2, 5 minus 4, 4, 9 minus 8 times x1, x2, x3 and I need to solve for a x is equal to 0 to obtain an equilibrium solution, right, and 0, 0, 0 is always a solution. Okay. So, 0, 0, 0 is always the one of the equilibrium solutions, but I want to know can I have any other solutions as well, and the answer to that comes from this fact that the equilibrium solutions lie in the null space of A. Okay. Equilibrium solutions lie in the null space of A. What is the meaning of null space of A? All the vectors which would satisfy Ax is equal to 0. Okay. They lie in the null space. So, a linear vector space whose elements are the solutions of Ax is equal to 0 is the null space of A. So, how do I determine the null space of A? Okay. So, I write A as 1, 2 minus 2, 2, 5 minus 4 and 4, 9 minus 8, and I now do elementary row operations to row reduce the matrix A. Okay. So, the first step would be to make these elements 2 and 4 0. So, I have 1, 2 minus 2. So, 2 times R 2 minus 1 time R 1 is 0, 1 time R 2 minus 2 times R 1 is 0, 5 minus 4 is 1, minus 4 0. Okay. Similarly, R 3 minus 4 times R 1, 0, this becomes 1, this becomes 0, right. Now, I need to make this element 0, okay. And how do I do that? Simply I keep the first row as it is, I keep the second row as it is, and R 3 becomes R 3 minus R 1, this is 0, 0, 0. Okay. So, now can I do any operation which would further row reduce my matrix A? The answer is no, I cannot do any operation which would further row reduce A. So, now I would convert my system of equations, my matrix back to a system of equations. So, that would be x 1 plus 2 x 2 minus x 3 is equal to 0. This is my first equation following the row reduced matrix A, and I have from second row x 2 is equal to 0, which means x 1 minus x 3 is equal to 0. Okay. X 1 minus x 3 is equal to 0. Okay, I wrote this equation wrong, so it has to be 2, and therefore, x 1 minus 2 x 3 is equal to 0. I missed the coefficient there. Now, I have one equation, x 1 minus 2 x 3 is equal to 0. So, I have one equation and I have two variables. I have one equation and two variables, which means now I can arbitrarily set one of the variables and that would fix the second variable. So, I say let x 3 is equal to some arbitrary constant alpha. So, this will make x 1 is equal to 2 alpha, fine. So, when I do this, I have now x 1 is equal to 2 alpha, x 2 was 0 and x 3 was alpha, right. Is this what I got from the previous analysis? Yes, from in the previous slide this is what you got. So, how can I write now x 1, x 2, x 3, x 1, x 2, x 3 is equal to 2 alpha 0 alpha, and I can further write this as alpha times 2 0 1. So, what are some comments which I can write about this entire system? What I can write is that the null space of A, the null space of A has dimension which is equal to 1. How do I make this conclusion? The way I make this conclusion is I look into this, okay, and I ask this question, how many vectors are present, and in fact, there is only one vector which is present, the vector being 2 0 1 transpose. So, when you have only one vector which is present in this final expression, then you say that the dimension of the null space of A is 1, okay, and a basis for the null space of A is the vector which is present. So, the basis would be 2 0 1 transpose. So the basis would be 201 transpose. So what do I understand by all of this? This simply means that if I have to solve for A x is equal to a 0 vector, A x is equal to 0 vector, then I know that 0 0 for the present 3 dimensional case, 0 transpose is always a solution. I know that. Now, I want to know whether some other solutions also exist. So, what do? I determine the null space of A. Well, I have determined the null space of A by the procedure which I highlighted. Let me very quickly recall the procedure. I would write the matrix A, I would row reduce it. Once I get a completely row reduced form, I would convert it back to the set of equations. I will analyze how many equations are there, I would analyze how many variables are there. So, I would do a degree of freedom analysis, which would tell me how many variables can be set arbitrarily, and on that basis the number of variables which can be set arbitrarily would be given some constant values, and the other vectors which cannot be set freely on the basis of the equations which you finally got would be expressed in terms of the variables which you would which you had set at your will. So, for the current case what you got was this. Okay. So, once you write this in the present case, for example, alpha times the vector 201, then you say that the null space has a dimension of 1, which means that if you know one vector, non 0 0 0, then every single multiplier would be solutions of your equations which would give A x is equal to 0. Let me repeat, if you know one vector which solves A x is equal to 0, which is still not 0 0 0 vector, then all the multipliers of this vector would be the solutions of A x is equal to 0. This is what you got from here. Now, imagine a case where you do the degree of freedom analysis as 2, and imagine a case where you get x 1, x 2, x 3 as say alpha times a vector say A B C plus beta times a vector D E F. So, in this case the dimensions of the null space of A would be 2, because there are 2 vectors, and the basis would be A B C transpose and C D E transpose, and the meaning of this is that A B C is going to be a solution of A x is equal to 0, A B C is going to be a solution, D E F is going to be a solution, and since these two make a linear vector space and A B C and D E F are the basis, then every linear combination of these two vectors would also satisfy A x is equal to b. So, therefore, it is not necessary that you have only one equilibrium solution which is 0 0 0 and so on. You can have infinitely many equilibrium solutions, you can have more than one equilibrium solution, and Now, whether that equilibrium solution is a stable solution or an unstable solution is something which needs to be determined. Previously, we determined whether the solutions are stable or unstable based upon having a look at the phase portrait. For example, when we drew for a first order system the phase portrait which looked like this being x and t and this being x, then we said that this equilibrium solution 0 is a stable solution because all the solutions are converging here. This was qualitative by looking at the phase portrait. In the subsequent lectures, we would take upon quantitative measures to determine how to establish whether the equilibrium solutions are stable or unstable. Thank you.